In this video, we're going to go over some basic limit examples that'll incorporate some of the properties that we talked about in the past couple of videos. So the first example is the limit as x approaches 3, x squared plus x minus 6 divided by x minus 2. So hopefully you'll see that the numerator can be factored here into x plus 3 and x minus 2. So x squared plus x minus 6 is x plus 3 times x minus 2. And in the denominator we still have x minus 2. And so using this division property we can evaluate the numerator and denominator separately. Plus 3 times x minus 2 minus 2. And here this product we have here is really the product of two limits. So it's the limit as x tends to 3 times x of x plus 3 times the limit as x tends to 3 of x minus 2. Then we still have divided by the limit as x tends to 3 of x minus 2. And at this point we can just plug in. So the limit as x tends to 3 of x plus 3 is 6. The limit as x tends to 3 of x minus 2 is 1. And the limit as x tends to 3 of x minus 2 is 1. So 6 times 1 divided by 1 is 6. Okay. Next example. The limit as x tends to 6, x squared plus 2x minus 8 divided by x to the 4th minus 16. You can see here trying to plug in 6 to all of this into this entire expression and evaluating seemed pretty cumbersome. Luckily both the numerator and denominator are factorable. Numerator factors into x plus 4 times x minus 2. The denominator is x to the 4th minus 16. That's the same thing as x squared plus 4 times x squared minus 4. But you can see x squared minus 4 is the same thing as x plus 2 times x minus 2. So I'm going to scratch this here. X plus 2 times x minus 2. Okay, so once again we consider the numerator and denominator separately. So the limit of this quotient, remember quotient's the answer to a division problem, is the quotient of these two limits here. And the numerator, both of these limits can be split up further. So this product here, the limit of this product is the product of these two limits. So we have the limit as x tends to 6 of x plus 4 times the limit as x tends to 6 of x minus 2. Denominator, we have limit as x tends to 6 of x squared plus 4 times the limit as x tends to 6 of x plus 2 times the limit as x tends to 6 of x minus 2. And at this point we can just plug in. 6 plus 4 is 10. Or actually, we'll notice here we can actually cancel at this point and see these two terms drop out, and we don't have to worry about division by 0 because we're not considering x equals 2. So we can actually get rid of these two terms here. So we have the limit as x tends to 6 of x plus 4. Well, that's just 10, right? 6 plus 4 is 10. The denominator, limit as x tends to 6 of x squared plus 4. That's 6 squared is 36 plus 4 is 40 times the limit as x tends to 6 of x plus 2. So that's 6 plus 2 is 8. So we have 10 over 40 times 8, that's 320. 10 over 320 is equal to 1 over 32. Now we're going to take a look at one more example. This one's going to involve a little bit of trig. So the limit as x tends to pi over 2 of the secant squared of 2x. And hopefully you remember from your pre-calculus class that secant squared of 2x is just another way of writing secant of 2x, the quantity squared. So that limit is equivalent to this right here, secant of 2x, the quantity squared. Well, that's secant of 2x is the same thing as 1 divided by the cosine of 2x. So what we have here, 1 divided by the cosine of 2x squared if you remember from one of our limit properties videos, the limit of something squared is equal to the limit of that something, the quantity squared. So the expression we have above is going to be equivalent to this expression here. So the limit of this thing squared is equal to the limit of this thing and that limit squared. Hopefully that makes sense. And moreover, what we have here is 1 over cosine of 2x, the limit as x tends to pi over 2 of 1 over cosine of 2x. That's the same thing as cosine of 2x to the negative 1 power. So as an aside, 1 over cosine of 2x equals cosine of 2x to the negative 1 power. And so when we're looking, so if we want to define, say, the roll down on the screen here a little bit. So if we want to define the limit as x tends to pi over 2 of 1 over cosine of 1 divided by cosine of 2x, that's the same thing as the limit as x tends to pi over 2 of cosine of 2x to the negative 1 power. But that's going to be equal to the limit as x tends to pi over 2 of cosine of 2x, and this limit taken to the negative 1 power, which is the same thing as 1 over, remember, something to the negative 1 power is the same thing as 1 over that something. So as 1 over the limit as x tends to pi over 2. Excuse my slanted writing here, but space is at a premium, so this is equivalent to this, and since this is equivalent to this limit here can be rewritten as this. So how does that pan out in the context of this problem? We're looking at here inside the brackets the limit as x tends to pi over 2 of 1 over cosine of 2x. That's the same thing as the limit as x tends to pi over 2 of cosine of 2x to the negative 1 power. Okay. And that limit is equivalent to the limit as x tends to pi over 2 of cosine of 2x, and that limit taken to the negative 1 power, which is in turn equivalent to 1 over the limit as x tends to pi over 2 of cosine of 2x. So this limit here is equivalent to this limit here. So what we can write is the stuff inside the brackets is 1 over the limit as x tends to pi over 2 cosine of 2x, and everything inside the brackets was squared. So now we can finally go ahead and evaluate this limit. So as x gets closer and closer to pi over 2 cosine of 2x, well, 2x is going to get closer and closer to pi, and cosine of 2x is then going to get closer and closer to negative 1, because if you remember, the cosine of pi is negative 1. And if not, I'll refresh your memory in a future video when I talk about the unit circle. So we have 1 divided by negative 1, quantity squared. So that's negative 1 squared, and that's just 1. So our final answer is 1. And that'll do it for this video.